Hi, everybody. So the first demonstration I wanted to show you is on this robot here. It's called Z1. It's from a Chinese manufacturer called Unitree. They're actually pretty well known in the community for building legged robots, so especially quadrupeds and recently also humanoids. But they also built a manipulator. This is actually supposed to go on top of a quadruped robot. It's very lightweight. It's very small robot, so a quadruped can carry it. But here you're going to see it just alone. And what we're going to show you is an implementation of a model predictive controller. So it's very similar to what we have been seeing in class last week. The main difference is that we are using a different solver. We are not using IPOpt because we are seeing that IPOpt is not really built for doing MPC, is more for offline optimization. And so we saw that we need to give it at least 3 iterations to produce something meaningful. Whereas with the solver that we are using here, we just give it 1 iteration every loop, and it works. So the robot is going to try to reach this object here, which we are tracking with a motion capture system, which you can see the cameras just above your heads. And in the meantime, it's going to try to avoid collisions, so self-collisions, so colliding with itself, collisions with the table, and collisions with this object, like this window object, which we have designed just to make it a bit challenging for the robot to reach the target while avoiding collision with this object. And what else? What's the frequency is 100 Hertz. Yeah. So everything is running 100 times per second. The MPC is getting new data from the motion capture to know where the target is. And it's recomputing a new control sequence, and that's being applied on the system. A little caveat though, this robot does not have a good torque control. So even though we can send current commands to the motors, and current is proportional to torque, the resulting behavior of the robot is not at all what you would expect because it has very high friction. Is it turned on? Yeah. Okay, so I cannot move it. Okay. Well, later we turn it off and we can try to move it by hand, and you will feel that it has very high torque. So it's when you have a very high, sorry, not very high torque, very high friction. And when you have large friction, it's very hard to have good torque control. So what we are doing, and what you would need to do if you had a similar robot in your hands, which are very common in industry actually, is to rely on position control instead. And so instead of sending the torque commands computed by the MPC to the robot, what we do is that we take the next state predicted by the MPC controller, so X1, and use that as a reference for the position control of the robot. In that way, it works. And another very important piece of information, we are not closing the MPC loop with the measured state. We are closing it with the predicted state. So basically, the MPC is entirely open loop, except for the position of the target from the motion capture system. And that's the standard setup if you're working with a robot without torque control. Then later we're going to move to the next lab, and there we have a robot with a good torque control, and I'm going to show you the difference. Okay. To get bigger every time if you don't have the loop closed. So the loop is closed at a lower level by the position controller. So there is no uncertainty growing, actually. The robot is going to track pretty well the trajectory that we give it to track. It's just that it's not going to be compliant to external disturbances. So if I try to push it, it's not going to let me push it. It's going to push back very strongly. Whereas the other one, we're going to see that it's going to be very compliant. So it's much safer in case you have human robots interaction. This one is not safe. Okay, well, it's not super dangerous either because it's not a big robot with very strong motors. It's a quite lightweight robot, so it cannot kill you. But still, it's not done for human-robot collaboration. Okay, we can start. Yeah.
Now it will move in a fixed position, and then I will start the tracking.
Okay.
Okay, now we're tracking the object. Then in a ring configuration, you can select
Quite aggressive.
on start. Now I think it was occluded for a moment.
And you can see how it's avoiding the obstacle moving back and forth. And everything is computed online just from having basically these three cylinders as obstacles in the environment. The optimization solver is finding a new trajectory that's avoiding the obstacles. The horizon, I think, is 35.
Yes,
So it's longer than the one we were using in the lab last time. And we can do that because we have a very optimized solver which can deal with such a long horizon. One iteration every loop, every 10 milliseconds. Of course, we use warm start, otherwise it wouldn't work. Sometimes there is an occlusion, so the motion capture system doesn't see the target, and so it gets stuck, but then it tracks it again, and then it starts moving again. So for doing self-collision avoidance, we are actually approximating all the links of the robot with capsules, which are like cylinders with half spheres at the two ends. And we are checking collisions between the capsules. Of course, it's also taking care of joint limits.
it's also very strict torque constraint.
Yeah, torque constraints for avoiding the torque limit of the motors.
What we do in a more comfortable configuration.
And this robot has 6 degrees of freedom, so the state is 12-dimensional. It's the same size as the UR5 we have been using in the lab sessions. Looks a bit like a snake sometimes. Okay. I think it's fine. We can stop it here. Do you want me to fold it? If you want to stop it. Yeah, sometimes it's vibrating. That's still low level position control. Any questions? Well, maybe you can turn it off so we can try to move it. So no, now the obstacles, they are supposed to be static. So they are hard-coded inside the solver, inside the problem formulation. Of course, if we were able to track the obstacles, we could also make them dynamic. We would just need to basically parameterize some inside the problem definition, the position and orientation of the obstacles, and we would adapt the value of the parameters inside the problem. The issue, if you have dynamic obstacles, though, is that you may know where they are now, but you don't know where they are in the future. So since you're predicting a trajectory that goes into the future, you don't know what's the future position of the obstacle that you should avoid. So in that case, you need to either be optimistic about it and so assume that they're going to stay where they are, or you can do a motion prediction. Maybe you can estimate their current position, velocity, and then you can predict how the position is going to change, assuming like constant velocity. Or you can do like robust MPC. And so you're going to assume that the obstacle can go in any possible direction and account for all possible future positions of the obstacle. But that can be very conservative, depending on how you do it. Any other question? Okay. So maybe you can come here now and try to move a bit the robot by hand. It just gives you a feeling for the friction torques that it has. Don't be shy, it doesn't bite, it's turned off. It's high friction.
Like you said, that it's low torque, but like what torque are we talking about?
The motor torque. I mean, it's low torque because it's a very lightweight robot, so it doesn't need. Do you remember the torque limits?
No, but I can.
Like a typical.
Yeah, like for the Euro 5, it was 150. I think this one is much lower.
But we set very low torques in order to make the task more challenging.
Ah, okay. Yeah, okay. Yeah, we also did that. We also artificially reduced the torque limits, which makes it also safer. And even with this low torque limits, you could see that it gives quite high accelerations during the motion. Yeah, that one is almost impossible to move. We don't know because it's not an open hardware robot. I mean, I can tell you for sure it has very high gear ratios because of the high frictions that it has. So probably it mounts quite small motors with high gear ratios afterwards to multiply the torque.
What is the maximum power consumption?
I don't have any idea. I mean, we can look it up, but I don't know.
written here.
Okay, just read it then. 500 watt,
360.
360. Okay, like much less than a washing machine.
Video.
Il video per la lezione.
Stavo pensando invece può stimare lo stato.
Okay, so this one is a very different kind of robot. It's called Franka. It's built from a German manufacturer. And this one, the main difference is that it has a very good torque control. So it's been designed for that, for having good torque control. The way it achieves that is actually not because it has no friction at all, but because it has torque sensors integrated inside the joints. So it can measure the torque that is being applied to the joint, and then it can do a very quick low-level feedback control that can regulate the torque with a very high accuracy. And this makes it a much more fun robot to work with than the other one, because here we can really do all the cool stuff we have been doing in simulation in class in the same way. So what I'm going to show you right now is what Filippo is working on. Filippo was actually in your place 1 year ago. It was a student taking this class 1 year ago. Now he's doing the master's thesis with me. And he's gonna, the goal of his thesis is actually to implement MPC. So the same MPC we have seen on the other robot, he's gonna try to implement it here and also introduce visual feedback. So having a camera mounted on the end effector to track the target so that we don't need all the motion capture system with the cameras above. But for now, just to get started, he implemented TSID, so QP-based control, what we have seen at the beginning of the course on this robot, and now he's gonna show us. Well, you can immediately see how the motion is much smoother without the vibrations that we had on the other one. So in general, this robot is much higher quality. And another big difference is that this is safe for human-robot interaction because it's torque controlled. So if I touch it, you can see I can very easily stop its motion. I just put my hand here. It doesn't apply much force because we're able to work with very low gains since we have a good accuracy of the torque control. I think it's tracking like an infinite symbol trajectory with the end effector. And this is running at 500 Hertz. So it's super fast, well, because it's just QP-based control, so we can run it very fast, much faster than the MPC. If you wanna try, I mean, maybe it's gonna be hard here to make everybody try, but if some of you wanna give it a try, just to touch it, to see how it feels gently. Don't push too much.
Yes. Oh.
It's very soft, right?
Thanks.
Gets angry after a while, so don't overdo it. So in your future, if you get to work with a robot, I think the main thing you need to understand when working with the robots is torque control. So is it a robot that achieves good torque control? If so, then you can do this kind of stuff where the robot is very compliant. You can send torque commands and it works. Otherwise, you are in the other situation where the robot, no way you're going to achieve a good torque control because friction is super high, doesn't have joint torque sensors. And so you need to rely on position control. And in that case, well, it's never going to be super safe to work with because it pushes hard in case of disturbances. And you cannot directly send torque commands because it's just not going to move, basically, if you send just torque commands. So you need to adapt the methodologies that we have been seeing in class to work with that kind of systems. And that kind of system actually is much more common in the industry than this kind. So just beware. It's more likely that you're going to work with that than with this. Okay. Somebody else want to give it a try? Okay, you push too hard. There are some security checks that if it gets pushed too hard, it just stops. That's why I told you to be gentle. No problem. I think Philippe is going to restart it. Okay, can try again, more gentle. Very soft, yeah. Anybody else? Last call. Okay. I think we can stop it. Thank you, Filippo.
But if I would grab something now with this rubber, I would need to adjust the board in that place right now, but it will be just like if I touch it. So I need to know what weight I am touching.
Yeah, you need to estimate, I would say, what weight you're lifting. Yeah, probably you would, especially if it's a relatively heavy weight. I mean, if you're lifting a pen, doesn't matter.
Yeah.
But if you're lifting like a 1 liter bottle, then it's 1 kilogram. So I think you would need to compensate for that, or you would need to increase the gains, which would make it less compliant though. So it's a compromise. But it's not too difficult to estimate the weight because you just grasp it, lift it a little bit, and then with just a few measurements, you can estimate what's the weight at the end effector. Because basically, since you know the model of the robot, when it's standing still, you know exactly what are the joint torques that you should feel. And the delta with respect to the nominal joint torques is going to be given by the weight. So it's going to be basically J transpose F, where F is mass of the object times gravity. So you know gravity, you know J transpose, you just need to estimate M. It's super simple. Just in theory, 1 measurement and you're done. So 2 milliseconds. Then if you want to be a bit more robust to sensor noise, maybe you take 10 measurements. But it's very, very easy to do that. So hopefully next year, we're going to show you also MPC on this one with visual feedback. Okay, I think we can stop here and we move upstairs to the class.